Welcome to History Valley Podcast. Today I'm moderating a debate/discussion between Jim Weninger and Dr. Aaron Adair on where does the evidence lean towards. This is a similar discussion that I hosted between Dr. Adair and Sean last time. I'll have the link in the description below so you guys can go check that out if any of you missed it. So today we're talking about a very similar topic. Does the evidence favor electric universe, or does the evidence favor mainstream physics? And these two gentlemen are going to be discussing, asking questions to each other on that topic specifically, on the evidence. The super chats are turned on, so if any of you have any questions for the guests, feel free to super chat, and I'll get the question up so you get your answers. Okay, so which one of you would like to go first?
Do we have a coin to flip?
Yeah. Jim, how about you go first, since you're pretty much the contender here. You argue against the mainstream understanding. You favor the electric universe view. So why do you favor the electric universe view?
Well, yes, as I was saying that even in the mainstream literature, there's a lot of evidence of electric fields that has been ignored. And so that's what kind of led me to be more open about the electric universe ideas. And again, recapping that article in 2001 in the Astronomy and Astrophysics Journal that said there must be an electric field. Basically, back in the 1920s, they worked out that there has to be an electric field at the sun's surface, just because in a plasma, in a gravitational field, the more massive protons are going to sink. And the point of the article, though, was that had even been forgotten in the mainstream literature up till that time. But even since then, it seems to be forgotten again. So we know that there's electric fields on the surface of stars from first principles. There should be anyhow. And also electric fields in shock fronts, and stars are formed in those. So like when I was in grad school, those ideas were already forgotten. These ideas that were worked with more in the 1920s, they had been forgotten. And we got to all these theories since then of like extreme collapse of like to neutron stars and black holes without getting to what was peer-reviewed mainstream ideas on electric fields. So that's how, that doesn't mean that EU ideas are right, but that means that something was clearly missing in the mainstream standard model of star formation and so on.
All right, so sounds like we both have a similar level of education, since I also went through grad studies in physics. What was your grad studies, by the way? I don't remember you saying before.
Well, my undergraduate degree was physics. Then I went to grad school for astronomy, but it was a small department. It was officially physics with a concentration, and the idea was to get a master's and then go on to get a PhD, which I never did. So you've got more education than I do, for sure.
It sounds like we had some similar experiences. I think we both found out the joys and tribulations of grad studies.
Oh, yeah.
But nonetheless, as was said, that I'm more in the mainstream. That basically means that on large scales, when we're talking about the formation of stars, galaxies, galaxy clusters, the primary driving force is the gravitational force. The electromagnetic force can't be said to have no role, but its applications have to be limited because of some of the fundamental things that we know about electricity, magnetism, the electromagnetic forces. It obviously comes into play if we're going to talk about the sun, because since the sun is a super hot plasma, if you try not describing the sun as the flow of charged particles, you're ignoring a whole lot of evidence. So we clearly need to be applying plasma physics in contexts like that. When it comes to, say, using that to understand how stars and galaxies form, not so much. And far and away, I'm distant from the ideas that we can explain the sun as generated by a giant electric current, and all the other stars in the galaxy are ultimately current driven rather than nuclear fusion driven. That, I think, is a point of contention we'll definitely want to be discussing.
Yeah, well, see, that's where my own area of expertise, if I have one, is on the local environment where stars form, like filamentary gas clouds, and the next level up, like the local chimney and stuff. And that's where, to me, the most evidence of electric current and all its ramifications, like Markland convection and all that, that's where they lie. Also, the magnetic fields, they obey where Donald Scott went with his model. And let me back up for a second. That's always been one of the main criticisms of electric universe theory, is that they're not mathematically rigorous. But then when Don Scott came up with that Bessel function idea, a lot that was lost on a lot of people because it was too mathematically rigorous, like Bessel function solution to the flow of charge. But once you see how that works, there's overwhelming evidence that filamentary gas clouds work that way and have those magnetic fields. The observations are out there to support it, but it's one of those things that's like totally, it's counterintuitive. Like an idea that you would argue against interstellar clouds being current carrying is there is no magnetic field wrapped around them by the right hand rule. I mean, we know that if that's how it worked, we would have picked that up in Faraday rotation observations. But what Don Scott showed is that when you have a lot of charge flowing together, it's the self interaction. It's basically the charged particles don't move just by the background electric or magnetic fields, but they interact. And that's where you get that Bessel function idea. And what it leads to is, and this is where I began to think that he might be right, is that leads to reversals in magnetic field direction. And because of my mainstream education, I knew how Faraday rotation worked, in that you need direct line of sight magnetic fields. And if you had reversing fields on a sight line, it cancels in the Faraday rotation. So that's why I realized that's why they wouldn't be seeing those. Even if you looked out at what looks like a filamentary current carrying gas cloud, you're not going to see in the Faraday rotation those magnetic fields. And that was pretty much where I started on that scale, though, just in local interstellar clouds. And I'll argue still that all the signs, like when we look at Markland convection, obviously that's not a mainstream idea for in astrophysics, because that requires current filaments. But what they do see is ionization gradients that vary with depth into these filamentary gas clouds. And you have mainstream models that try to explain it, but they don't work. For example, with the Markland convection idea, there should be cylindrically symmetric ionization distributions. What the mainstream sees is that, but what their model was that maybe it's stars out there shining on the gas clouds cause photoionization. But what that should cause is hot spots near these ionization sources, and not a cylindrically symmetric. Basically what I'm saying is the observations on the scale of interstellar clouds are exactly what are predicted by this mathematical model that Don Scott came up with, and Markland convection, and on and on. But the problem is, in the EU community, there are a lot of people that don't want to get too mathematical and technical. It does attract a community that's against mainstream science, that has, for other reasons, like religious reasons or whatever, challenged mainstream science, and they just want to take the idea that, okay, these other guys are right. But on the other hand, there's not a lot of mainstream scientists with good mathematical background that their tendency is to say pseudoscience and not even look into it. See, that's where you and I are on the same page. The fact that you're willing to debate me on this topic means that you are willing to entertain the ideas. You might not agree with them, but you're not just going to laugh it off and then walk away and just say, it doesn't fit with the mainstream, therefore they're quacks. Okay, I'm talking too much now.
I think it's appropriate because, as Jacob mentioned, that you're quote unquote the contender, and I want to make sure that your views are well represented because, like you've mentioned, that there's a bit of community in EU, that there is a diversity of views. Like I mentioned before in the pre-show, that as I understand, some are so extreme that they completely deny the existence of gravity. So with a spectrum like that, I definitely am glad that you expressed yourself clearly that way. On the other hand, I think you also used a fair bit of terminology that the audience listening to may not fully appreciate. So if we talk about Bessel functions and line of sight vectors and things like that. So if I can try rephrasing what you said, just make sure I have things correctly, that when you're talking about filaments, you're basically talking about what looks like clouds of gas and dust in star-forming regions. And the idea is that these are actually traveling plasma, so they're carrying a current. And because the current is strong enough, it's able to do such a strong magnetic field that it can confine itself as it travels, right?
Right, as opposed to the idea that they're all just formed by gravitational collapse and then held together also just by gravity, as opposed to having double layers at their surface, which, again, they don't have to be current-carrying filaments to have double layers holding their surface together, but that's still another electric effect that we're talking about.
All right. So instead of being dismissive or wondering how such things can form, my question would have to be with such a thing: what sort of test can we do to actually see that these filaments are moving at the sorts of rates needed to actually maintain such a magnetic field? And then, of course, what other evidence can we see that these are actually charged particles moving through? If it's a plasma, that it's charged and to be moving fast enough to have a strong enough magnetic field to confine itself. We're talking particles going at relativistic speeds, I would say. So what are the observations that we should expect to see if that is true?
Well, there's again, that Bessel function idea is really critical too, because if you understand how that works, it means that there's even going to be current reversals. Basically, how it works is the logic of it is that instead of all the charge flowing in the same direction that's the background electric field and spiraling uniformly around the background magnetic field, that because these particles interact with each other, you get these crazy, even electric current reversals across a filament. You'll still have a net. Again, I'll be very cautious here. If Donskotz and Lundquist before him had the same model, which is a good hint that it might be onto something when they came up with it independently, and then Donskott only realized later that it was the same theory again. But what it means is that you would have these shells of charge moving and then shells moving back the other way. Still a net current for the whole thing, but locally you might see different streaming, and you'll also see magnetic field reversals. And all this stuff is out there in the literature, but you almost need a EU to mainstream. A lot of times when you're talking about behavior, well, like I was saying with Markland convection, that's an EU idea. or a mainstream idea when they're talking known electric currents in a plasma. But in the mainstream, you might see ionization gradients. It's the same thing as Markland convection, but you'll never see, if you don't know the mechanism, then it gives you different terminology. And you see that over and over. Like people in the EU, you don't talk much about scintillation screens. Now in the mainstream, you know that scintillation screens are caused by free electrons. And if you see scintillation screens moving along the surface of gas clouds, people in the EU should be really excited about that. You know, that's the flow of electrons that can be matched to the surface of a cloud. The mainstream, not into the EU ideas. People in the EU, not enough versed into mainstream, even terminology, to know that if their observations are supported, you don't know where to look. And that's where kind of my background, I read mainstream just like you do. We know what we're seeing when we see these technical articles and the math. We kind of know what it says. And a lot of people in the EU community don't have that part of it. They don't have the mainstream term. It's a language difference, you know. But the evidence is overwhelmingly, I would say, just for interstellar clouds on that scale, that they are current carrying, they have the magnetic field reversals and those signs of Markland convection that we need if those are current carrying clouds.
I think I need to rephrase my question a little bit. Like, what observations are we able to do with telescopes? What are we looking for that we can see, oh, this is expected on charge-carrying filaments and otherwise unexpected on gravitational collapse theories?
Well, with as far as like magnetic fields, as far as electric fields, you should have a Stark effect. I mean, that should be a clear one. Like if people in EU are arguing strong electric fields, they should be seeing Stark effects. And being skeptical, again, more mainstream when I started, I'm like, well, we would have seen those we would have seen Stark line splitting in stars, for example, or compact gravitational sources. But the problem is, you get this idea that things are a lot simpler in observations than they are. I mean, we have lines. We know that we have the Zeeman effect. There's the Stark effect. There's actual Doppler motions, you know, from stars spinning. And other than the closest stars, they're pretty much point sources where we interpolate. Like we even get the shape of a star from how much redshift and how much blue shifted, like rotation rates, thermal up, like on the sun, we think there's thermal updrafts and downdrafts. And so you have a lot of ways to explain the same behavior. And what you find we tend to make it all match whatever theories we believe. If you don't believe that there's Stark effect on the sun or other stars, then you're not looking for that line splitting that way, and it's going to get masked. And like I say, all this should be a takeaway for anyone not into EU, but with a little bit more overconfidence in the mainstream model. No, they don't really have this stuff all mapped out clearly. It's a mess on the surface, even of the closest star, the sun. There's a mess of lines that we just interpret the way that we think to match the model, but it's really not that straightforward. So you can't argue that you can't really argue that there's no Stark effect line splitting. But yeah, again, I'm getting away from your observation, more your question saying more what not to look for, or what we can't simply look for. But we should be looking for magnetic field reversals on regular distance scales, and that appears in the mainstream literature. They describe it as magnetic turbulence, but if the electric universe ideas are right, that's going to be more uniform than turbulence and should appear in other clouds, since they already found that interstellar clouds form on fairly regular widths. That's an unexpected result of gravitational collapse. Now, there's other ways you could try to explain it, but in the EU model, that means they should have the same kind of magnetic turbulence. In other words, these same reversals on the same distance scale. Now, that hasn't been done yet, but that would be proof, or not proof, but evidence at least, that the electric universe ideas are right. And another one, this is a clear one that I've been pushing for a long time, is that you're familiar with the double helix nebula, right?
Mhm.
That's one where the EU model makes a hugely different prediction that we could test but hasn't been tested, but it is easy to test. In the electric universe idea, those stars are spiraling along the filaments. And since those twisted filaments go across our field of view, we should see stars if the EU ideas are right, we should see stars coming towards us on one side of that axis and moving away on the other side. And we can get that just from looking at the spectrum. Now, the mainstream description of the double helix nebula is the stars are just being shot out pretty much in a straight line, and it's only the nebula itself it's a magnetic torsion wave being wound up behind them. But that's an easy one if somebody would take the time to look at those stars and see if there's a systematic redshift. Either the stars are all moving about the same way towards or away from us, or stars on one side are spiraling helically towards us and stars on the other side are spiraling helically away. And here we could get away from any of these other arguments. Are there other things that cause redshift? It doesn't matter. Like our stars that close to the center of the galaxy systematically redshifted. It doesn't matter, because what we're looking for is a difference in redshift from stars on one side to the other. So that's an observation that, to me, will conclusively, when they're made. Ironically, though, here again, we're in that situation where it's only people really in the mainstream. You have to be able to lock onto a star and get these spectra to see the redshift and blue shift. That's not going to come from some interested person in EU reading on their Thunderbolts forum or something. That's not going to come from them. That's going to come from mainstream observations. But no one in the mainstream is looking for that, because they already have their mind made up how those stars are moving. But I'm going to say in advance that they're going to find that these stars are spiraling in that way. And locally, this is what I found. Now, this is something I can prove without EU theory or standard model theory, just by star motions. The Sun and Altair and other local stars are moving around Arcturus. And you get that just if you use Arcturus for a center, the radial velocities of all these stars drop out. It's the same argument we use in the early days of the solar system, when they thought that whether the sun or the earth was a center, they didn't need Newton, they didn't need Kepler, they didn't have any idea of the mass of the sun. How they knew what the right center was motions alone. If you pick the earth as a center, you get this crazy motion, like Mercury might be moving towards us on one side of the sun, it might be moving across the sun with high proper motion, then radial velocity way. If you pick the center as the sun, all the radial velocities of the planets drop to a minimum. I did the same thing with local stars And I found that, yes, if these stars are moving around Arcturus, there's no other way around it. And that's one, again, I think can be, if you're in the mainstream, you would want to you can't use a black hole there because other stars more locally aren't spiraling around. That's where you would want to go with your dark matter. You could say that there's a shell of dark matter around Arcturus, for example, and then that would explain how these are bound. And that was done on a larger scale. There is a ring of stars, much larger scale, like 1,500 to 2,000 light years across, a ring of hot blue stars circling us, and it's bound. It seems to be bound, or at least weakly. And there's a theory of dark matter, that it was a clump of dark matter passing through our galaxy in our neighborhood, and that's what caused it. That works. But here's where the dark matter stuff gets messed up, is if you want to explain galactic rotation, you can do that with whatever distribution of dark matter, and it requires very little, and definitely not clumps of it in the solar neighborhood. Now, if you want to explain this local ring of about 2,000 light years across with a clump of dark matter, that works, but then you better go back and patch the rotate. You better have evidence of that, or explain why it doesn't show up in galactic rotation near us. But now if you want to take that down to the scale of put enough dark matter that would keep the sun bound to Arcturus and Altair, you now have it inside this other ring of stars, and you better explain how that doesn't show up there. And that's where, again, I argue that the EU ideas are really important, because you can't have, with the local chimney, we have a structure. That's what I've been on about for a while, that scale. There's this hourglass shaped chimney where all the neutral matter is pushed out to the outside, but right around the narrowest part of the hourglass is where we see this ring of hot blue stars. That's like almost perfect example of a plasma pinch and a torus around it. And the motion of the stars, there's a stream of stars down through the chimney, and then there's this ring of hot blue stars around right where you would put the most current in a plasma pinch. And I've argued that that structure alone is evidence of electric currents and a pinch. It's a beautiful example of a pinch with the motions, star motions, matching the distribution of where we see the neutral matter, and then even the Pleiades cluster seems to be right down in the center of that pinch, and that's where the Pleiades distance problem, again in the mainstream, that not a lot of people in the mainstream want to go for, and that this is one that was important to me. And again, you don't have to be in the EU to know this. The Pleiades distance problem was that basically Hipparchus, which was set up to do distance measurements, got a shorter distance than Hubble. But if you look at the mechanisms they used, Hubble was using relative parallax, looking past the stars to get the distance, and Hipparchus was using direct parallax. But those answers would be different in the way that they were, as if there was light bending around the Pleiades. And that should have been an intuitively obvious answer in the mainstream. But why they didn't go there, there's not enough gravitational mass in the Pleiades to bend light that extreme, so you don't even consider that option. But there's also not enough gravitational mass there to cause that ring of hot blue stars to rotate around it. So, in other words, there's already something, forget about EU for a second, there's something fascinating going on there that is just explained away, even in the standard model. Like the Pleiades distance problem, the way it finally was resolved is that one of the teams was right and the other one was wrong, and that somehow Hipparchus, even though the whole point of that mission was to get accurate parallaxes, and that distance is really short it's where parallax distances should be pretty dead on. That should have been one where the mainstream went in and said, wow, this is not who's right and who's wrong. Why are direct parallax distance measurements different than relative? But again,
Okay. I think we might have gotten a little bit distant from what we were talking about earlier. So if I could jump in a bit.
I'm sorry. But
Yeah.
again, the general summary of that is that the things that you would expect in a pinch and the way the electric ideas work, the evidence for that is on that scale. Like not so much. Like when you go out to talk about like galactic rotation curves and the expansion of motion in clusters, the problem is there's a lot of ideas that are questionable that we can't confirm. Local stars, we know how they're moving. With galactic rotation, that comes from redshift, but now you end up with that circular thing where there's some that question redshift and whether redshift can only be that Doppler redshift idea. And then there's some that question dark matter, but what you see in the mainstream defense is we know that there's dark matter because of galactic rotation curves. And how do we know galactic rotation curves? From the redshift. But then someone says, well, how do we know that redshift is right? Well, we can see it in galactic rotation curves.
Hey, Jim.
Yes.
Let's let Dr. Adair respond to some of the points you've been making, because you have been talking for a while.
Yeah.
No, that's okay. It happens. But let's let Dr. Adair respond for a little bit.
All right. So I was first having us talk about the filaments as currents, and I was asking specifically, like what sort of observations we can make, because one of the things that I would expect if there is some fast-moving charged particles traveling through, especially in enough abundance to be seen with our telescopes, then one of the effects that we should see is going to be a form of inverse Compton scattering. Usually it's called the Sunyaev-Zadovich effect. If just so the audience knows, this is an effect that has been known since about the 1930s. Basically, when you have a charged particle and a photon coming in, have light coming in, when it bounces off, the light won't have the same wavelength, the same frequencies it had coming in. In particular, if you have a charged particle coming in at very high speeds, it's going to actually increase the wavelength of the light that bounces off of it. And this is actually something that's studied quite a bit in astrophysics. And it's actually quite important. It's something we actually scan for a lot. For one thing, we actually use it to discover and identify new clusters because there'll be some sort of hot plasma there, and then light from the cosmic microwave background will go through that, bounce off those high energy particles, and then come off at a different wavelength. So we can see that effect and identify those structures. We actually need to do that when we're trying to reconstruct the image that's created of the cosmic microwave background, which is usually said to be the afterglow of recombination, which took place almost 400,000 years after the Big Bang. Key thing, though, is there's this background light throughout the universe, light bouncing off fast-moving charged particles should change the light, and we should be able to see that. And we're scanning the entire night sky to create this map of the cosmic microwave background. So when scanning, if we're not seeing that effect, it's because it's not there. So there have already been scans over the filament regions that you're talking about and not seeing the SV effect, that inverse Compton scattering effect, which would be highly expected if that were the case. Moreover, if you have high-speed charged particles then going into other sources of matter, such as stars, then you would also expect to see a huge amount of radiation in that case, because you would have charged particles crashing into something and giving off either synchrotron or Bremsstrahlung radiation. And again, I've seen no evidence that seems to exist as well. And these are things highly expected on the idea that these are fast-moving charged particles. Since we don't see that, that is actually strong evidence that it is not some sort of charge-carrying phenomenon, at least nowhere near the levels that EU would suppose, especially when often they're talking about currents of 10 to the 18th power amperes, which would be so gargantuan the effect could not possibly just be hidden from these sorts of observations. So that's something I would look to and say that's extremely strong evidence against, while conversely, the formation itself is completely understandable from gravitational collapse. It's gas and dust that's naturally gravitationally attractive, and so it's falling in to form these filament structures. So because that evidence can be explained on either theory, and there's observations that we would expect if it were charge carrying that we don't see, it's then strong evidence against being explained as EU proponents would.
Yes, again, if we go back to, that's why I looked into, again, that Bessel function model, in that there is a huge amount that does different, even for, if current filaments, I mean, we're even talking about like focused, smaller scale filaments, if they really have this Bessel function field, magnetic field, then you see right away what that does to the idea of like cyclotron radiation, for example. The ideas that you get for a charged particle spiraling in a background magnetic field, that's pretty much introductory physics. But they always assume a fairly uniform magnetic field direction. What they don't get into at all is a Bessel function magnetic field, where the magnetic field rotates with radius, from being wrapped around in one direction to wrapped around in the other direction along the field, parallel, anti-parallel. That's the Bessel function model. And one of the primary indications things about that is it really messes with the standard model of how a charged particle spirals in a magnetic field. If you can't have a charged particle spiraling in a magnetic field if the magnetic field itself reverses multiple times inside that cyclotron radius, for example. So that's another one where if that model was right, again, I'm trying to keep it as a debate, not that I know what's going on, but if that model is right, you have to rethink, like I said, evidence of Faraday rotation, that cancels, but cyclotron radiation is suppressed because of, you would only get the energies where the charged particles spiraling very tightly around a local field with where it doesn't have any time to change direction, basically. So that also has to be readdressed. And again, I'm really open. I like getting people with a mainstream background to see the implications of this, and then you tell me how this, what we should be looking for there. I know what disappears in each case, but I'll argue that that's why we don't see a lot of that. And to the extent that we had force-free filaments, I know that's a EU model. That's very much an oversimplification. But in that model too, where charge is, to the extent that charge is moving along local magnetic field lines, then you don't get any of those effects either. So that's like a whole nother issue. Now,
the thing is, though, the descriptions that you're giving of the distribution of the charges or the distributions of the current flows, that would not really be relevant to explaining away not seeing the SV effect. We see that with completely amorphous collections of plasmas in galaxy clusters. It just simply follows from having things moving, charged particles moving at relativistic speeds, encountering light, and the light bouncing off and gaining some momentum in that. whether they're going coherently or incoherently or in any sort of spiral pattern. Nonetheless, you're going to expect to see that SV effect, and we have not seen that, and we have scanned the whole sky looking for these sorts of effects. If it was literally right here in our galaxy, we would have seen that in our surveys by now, because we have tried mapping out galaxy clusters and these hot plasma clusters far, far away from our galaxy when we're trying to clean up and have a proper map of the cosmic microwave background. So if there was literally something here in effectively our galactic background, and we're not seeing it, then that is extremely strong evidence that it's just not there. And giving a complicated description of how it's moving doesn't take that away, because it follows from much more fundamental physics.
Yeah, well, see, the problem with going with the cosmic microwave background already, and you're familiar with this, the axis of evil problem, right? That the cosmic microwave background seems to align both with the sun's direction of travel and also with the ecliptic plane. There's a lot of articles written on that. Why should the cosmic microwave background be aligned with anything in this our solar system in any way? That should have been the first hint that you're not seeing cosmic microwaves. Now, that doesn't mean that we're not. There's evidence that cosmic microwaves come from far away. There's imprints of that for sure. But the right way is not looking at that as the cosmic microwave background. If we know that there's effects aligned to our solar system, that means those are local. That should be an obvious, like a no-brainer. If you see that the dipole is aligned with our solar system in any way, that's the scale you want to put it on. Now, that doesn't mean that there's not microwaves from other sources out there. Whatever's causing that here, if you want to put it on local filaments, then other galaxies have those too. So yes, there is going to be a general uniform background to the extent that's, but that's how you know that that idea also wasn't right. The fact that there is this chance.
I would like to stay just on the filament thing for now, just because my point wasn't even related to what is the cause of the cosmic microwave background or any of the theories from that. Just simply that in our process of trying to map that out, that included finding all the sources that would give off the SV effect light that I'm mentioning. And the fact that we haven't seen that from the filament structures that you're talking about means that we have looked for that sort of effect, not seen it locally, and therefore we have very good reason to conclude we don't have relativistic charge plasmas traveling in these filaments. Whether the cosmic microwave background is due to the afterglow of recombination, or is just some guy with a flashlight 1,000 light years away, whichever reason that is, it doesn't even matter. Nonetheless, the light coming from that source, bouncing off charged particles, moving at high speeds, is going to have the expected effect. There's going to be momentum imparted in the same sort of way, like the basic physics of like billiard balls hitting. You're going to expect to see the momentum change after that collision. We're not seeing that effect, and that is not expected if there isn't this plasma stream that you're describing. So it doesn't even matter like what Bessel functions we use to describe it, what the source of the CMB is. It's nonetheless an observation that is failed to be found.
Yeah, I'm definitely open. I'll look into that more. But the idea for the microwave, this again, and it is important if you're going to talk about signatures. We see it, in that sense, that's a lot of what we're looking at. We know, even in again, mainstream theory is where do you get microwaves locally? Anywhere a hot sparse plasma meets a dense wall of neutral material, you get microwaves. We know that we're in, we can see that we're in one. The cosmic microwave dipole happens to align with that. That should be a no-brainer in mainstream model, that we know what causes microwaves. We see a microwave alignment to that. But then that means right away that you're talking about, look, you're talking about observations that don't even go on the right scale. You have to get that part sorted out out first before we're talking about like where there are these or aren't these electric fields, at least what you see in a microwave, in the cosmic microwave background signature. You better know where that is before you even argue that. Now, I'm not trying to sidebar from your comments. Are an area that I really do have to go back to the literature. I don't have an answer. I mean, you win that point very clearly.
Okay.
But I'm not content to let that one go. Maybe you and I can revisit that. But,
Okay. I do also want to note that the dipole that you're mentioning. So, Jacob, I don't know if you're able to bring up an image for us, because if we're talking about dipole moments for CMB backgrounds, this is not exactly common knowledge. They're not like pictures of the Kardashians that everyone recognizes instantly. For better or for worse.
So what was it you were talking about again?
So it's called the cosmic microwave background, or CMB, and it's called a dipole. Basically, it just like with a magnet, there's north and south. There's some sort of sense of directionality. If we want to bring up some image of what that looks like, so it's an effect that yes, we do know and recognize, but the mainstream interpretation of it is that it's due to the motion of our galaxy in the local group, usually called something towards the great attractors. So
is
that
it
sort of motion.
an electric dipole?
It's not
cosmic
white, but
Cosmic?
I think if you look up axis of evil problem,
Okay,
and just go to images, I think there's like graphs, like somebody made a good presentation on it for like mainstream science, just to illustrate the issue, like why it's such a, and it shows like the hot lobe and the cool lobe of the cosmic microwave background. And
right. And the mainstream interpretation of this is due to motion of our own galaxies in the local group. And it's an amount of redshift they were expected if we're moving at about like 600 kilometers per second or some, wicked fast speed. I try saying wicked fast, and I'm trying to pretend to be Bostonian. But it's interpreted in that sort of way. So it's not something that mainstream cosmology ignores. It's explained by local motions of our galactic group.
It's just that in the mainstream cosmology, that's highly coincidental that it should align with, like if it really is that's the direction that our whole solar system, for example, is traveling through space. Why should it be that our sun has our sun's local motion has anything to do with that, or our ecliptic plane has anything to do with it? Like that's highly coincidental. That's like puts us in a special place. It could be. I mean, we could.
I will say I've never heard anyone call it the axis of evil. That sounds a little too George Bush for me.
Yeah, actually, that's in the peer-reviewed. That came from a peer-reviewed article where they were looking at all these alignments and across scales and seeing why, like, it did give someone headaches, and that's why it caused that. But yeah, it shouldn't. It would be. Oh, go ahead. I'm yakking too much.
Oh, I was going to say the level that we see from it, that it's like when we map out the whole thing, it is consistent with basically having redshift in one direction, blue shift in the other, due to local motion. So, and just so everyone, again, we have a lot of non-physics audience, so let's. I'm going to try to make this as inclusive as possible. So, the redshift and the blue shift, this is a phenomenon that light has when you are having some sort of moving source. We probably know this at the Doppler effect when it comes to sound. When a train is coming at you, or a bus or truck is coming at you and it starts honking, it's higher pitch sounding than when it's moving away from you. A similar sort of thing is going on with light. When a source is coming towards you, the frequency of the light increases, the wavelength decreases, it becomes bluer. And when it's moving away from you, it's redder. So this dipole that we're seeing when we're trying to map out the background radiation of the universe, we see that basically it looks like we're going towards one direction away from another. And this overall effect is then explained by the local motion of our galaxy cluster. And thank you, Jacob. This image is also when we try mapping things out. So when we take into account the local motion of that and subtract out that effect, What we have in the middle is then an image you have. So that bright spot of red down the middle, that's our galaxy being in the way. And so when we then try to subtract out that effect, what we get in the background is the afterglow of an event we call recombination. So the mainstream interpretation of this is early in the universe is stupendously hot, so hot the universe is all plasma, and there's like no significant like free path that light can travel through. The whole universe is opaque. So if you try shining a flashlight, that light won't get very far. Once the universe is expanded enough and cooled down enough, electrons and protons are able to cool down enough and form atoms, and then light can actually freely pass through space again. And the release of those photons from that period called recombination, when the protons and electrons were recombining, is then this overall effect that we see across the entire universe. The hot spots and cold spots in there are very, 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 very tiny temperature fluctuations in those measurements. The overall temperature is about 2.7 Kelvin, and the fluctuations, we have measurements down to hundreds of thousands of a degree, hundreds of thousands of a Kelvin. They're very small, tiny fluctuations, and the study, the statistical distribution of these very small structures has been of supreme interest to cosmologists for at least 30 years with the COBE satellite, which I think is responsible for the ultimate image on the bottom, but I'm not 100% if that's COBE or a later mission. COBE was a satellite, a space telescope from the early 90s. And then there were newer versions such as WMAP. The most recent one is Planck, doing more and more and more refined measurements of the cosmic wave background. Yeah, and I think the top image, it looks like it might be from WMAP, but some of the structures in there I'm not so sure about. If that's also after effects from the Milky Way being in the way, I'm not quite sure. It's a little different than the maps I normally see.
Yeah, see,
I hope you guys all wanted a lot of science this hour.
See, the issue was whether then why it was such a headache is that why should, if it is cosmic scale, why should the sun's local motion or orientation of our solar system have anything to do with it? And that's in the mainstream. If you want to accept all the theory, then that still is an unresolved problem. It either is a coincidence, which it could be, or there is a mechanism for it, and or I'm correct in that they're putting those microwaves on those microwaves anyhow on the wrong scale. Now, one of the problems with that whole idea is that this is where physics kind of, it doesn't grow up in the right order. People just make discoveries after other theories are stated. Like that idea of motion causing redshift and blueshift absolutely is correct. And we can see that in orbiting binary stars where it might be blue shifted coming towards us and then red shifted going around the other side. But there are other sources of, it took laser optics guys to start and then plasma guys to realize how all these other sources of redshift and blue shift. And the one that matters most, that this isn't mainstream theory, but if free electrons in a hot sparse plasma cause redshift, then where we have a lot of free electrons, like in shock fronts, should be redshifted. So where we have jets coming out from galaxies, there is actually a mechanism that laser optics guys know about, that astrophysics guys in astrophysics, and I'm saying that
Oh, I think we might have a connection problem.
Doppler shift, and it's not.
Basically. Oh, Jim, we lost your sound for about 10 seconds.
Oh, okay. Well, that's probably a hint. Again, I'm talking too much. I'm just arguing that there are other effects that we now know about that cause redshift and blue shift, and this isn't that extreme. Like you get there are some in the EU community that deny actual Doppler. That is absurd. We know they work, and we know it's pretty pretty accurate too. Not a lot of room to add, in most cases, a lot of room to add any other redshift and blue shift. But there are observations out there that do make more sense in these other discord. This is where Halton Art went off track a while ago. He did have observations that the redshift didn't match mainstream theory. Unfortunately, he went on to, he also not a
Having a bit of
why
connection
that.
trouble.
Okay.
Sorry, we had some more connection trouble. I think the internet's getting tired tonight.
But I was just arguing that I'm not arguing that ARP was right on his mechanism, but that some of his observations do need to be looked at with other mainstream, not astrophysics, but other mainstream physics ideas of redshift and blue shift. And until we get that totally down, what all the mechanisms for redshift and blue shift, and we shouldn't be always interpreting those as those extreme redshifts, especially as space velocities, not unless it works. And in case of the axis of evil problem, there are hints that that's not the right interpretation. And again, I'm not arguing which it is. I'm just saying that that was another mistake that we learned in school. It's just jumping right to redshift and blue shift is Doppler shift. If it doesn't match what we see here, then something's moving towards and away from us. That's not always correct. And we know in physics that's not correct. But now I'm totally off the topic again.
Along the way, you also mentioned something with laser optics, and it gave me a thought. What do you think of the LIGO observatory?
That now the search for gravity waves.
Mm-hmm. Right. Just to make sure, is he freezing or am I the one frozen?
He's the one that's frozen.
Okay.
Just give him a minute.
No problem.
He didn't lose complete connection there. He looks like he's not unfreezing this time.
All right. Just for the audience sake, the thing I brought up, the LIGO observatory, this is the Laser Interferometry Gravitational Wave Observatory. There's a couple of them in the US, and they are these monumental structures that are designed to look for the effects of gravitational waves. The basic idea is because light is a wave, when you have two light sources the same wavelength coming to each other, you can get wave patterns where a crest of one wave and the crest of another add up, and you get a brighter wave, deeper, trough and trough deeper, darker, and also complete interference and blocking out. So yeah, LIGO is trying to look for extremely subtle effects due to a passing by gravity wave and ever so slightly changing basically the shape of the structure there, and trying to use that to see if there's anything basically oscillating space-time itself. I was just telling the audience what LIGO was supposed to be doing.
Okay. Am I coming and going again? Yeah, what I'm not one of those that doesn't believe in gravity. And I was even looking at
It looks like he froze again.
And okay, sorry about that. I might be breaking up too much. But yeah, even in a Lesage type theory, not saying that that's right either, you would expect gravity waves. If gravity was some kind of pressure in a medium, why we got Einstein's ideas. He was brilliant in that he knew right away that if gravity propagated at, light-like speeds, there would be this orbits in our solar system would quickly decay. So one of the beautiful parts of Einstein's theory in the beginning was that gravity didn't propagate. It instantly, everything knew where everything was. Space was curved. That one, those original ideas were the most against the idea of gravity waves. Lesage type, pressure-based from an ether, that allowed for waves, just faster than light speed waves, though, in that case. But yeah, I'm just saying, I do accept that there should be waves, in whether Einstein's view is right or not. And no, I absolutely don't think that gravity isn't real, or that it. I believe we should detect gravitational waves because gravity propagates in a medium and not in the vacuum of space. So, yeah,
I was bringing it up as well because earlier you seemed to have a bit of antagonism towards compact objects like neutron stars and black holes. And LIGO has detected multiple mergers between black holes and neutron stars with neutron stars.
Well, actually, yeah, they think they have. I mean, that's based on, obviously they haven't seen black holes. So what they're doing is calculations showing that if there are two massive black holes, you can work out then that they're not actually seeing the black holes or even other evidence other than
Okay, so
accretion disks and jets, and then you saw, then that would be, I would accept that that's actual evidence of that.
Okay. The thing is, though, several years ago, there was a pretty darn good confirmation of the merger of two neutron stars because I think this was back in 2017 that LIGO detected the merger of two neutron stars. They're both around two solar masses. And it was confirmed by multiple optical standard sort of telescopes. It was confirmed about a second or two after seeing the gravity waves that there was a gamma ray burst. Then there was there were dozens of other telescopes around the world that looked and saw the after effect of that collision, because with two neutron stars colliding, it produces the sort of effects that we can find the radioactive products that it shoots out, and then look for the radioactive decays of those elements from neutron capture. So that's an example where it's not only just the observations from LIGO, it's actually a combination of multiple gravity wave observatories and dozens of optical telescopes or other light wave telescopes all looking in the same spot and seeing the same object appearing in the same place at the same time, with all the evidence of looking like what you'd expect if two neutron stars merged together and had a really, really big explosion.
Yeah, see the problem I have with neutron stars and black holes from even for the formation is you already have to ignore, like I say, they have that idea of charge separation. Is if, I mean, you see all the arguments that matter's gravitationally tidally torn apart as it falls into a black hole. There's nothing about charge separation, and no follow-up to that idea that more massive protons will sink deeper into the plasma around it. Forget about the actual surface, which we're talking about. You're going to have insane electric fields then. If you even want to address the theory right, again, just from where we were with where we left off with stars, that a mundane star like our sun has an electric field. A white dwarf should have a huge electric field at the surface. You know that if you're talking about modeling gravitational collapse into a black hole or neutron star, and you're not talking about the insane electric fields that would have to be generated, and there's not. I'm quite aware of mainstream theory on that's where I was, and that was the interesting topic in when I was in grad school, is black holes, and I didn't consider myself the genius to do that. So I just went to all these cutoffs, like what objects would be black holes, which ones would be, neutron stars, which ones would end up in, like burned out dwarf state and all that. But there's nothing in the theory even talking about gravitational charge segregation. So you know that the theories are fundamentally wrong in that respect. I mean, and again, that whole aspect was ignored since the 20s. We've got the more recent article in 2001. It obviously nobody read it because it was ignored again. And so you know that the theories there are not right. We should.
So I want to push back on the idea that it's ignored, therefore the models are wrong. When a paper goes out and it gets ignored or it doesn't get much traction in the community, that isn't necessarily because no one has any good response to it. It could be something simpler, like they read the paper and it's like, it's so flawed or its assumptions are so simple that it's not applicable. So for example, you mentioned earlier that it's a very simple model that doesn't account for things like the rotation of the sun. It also sounds like it doesn't take into account the fact that there are major convection currents in the upper layers of the sun, which means it's going to be doing the sort of mixing. So they're not going to have this separation of electrons and protons because of their mass. So I would just say, well, the reason that model isn't being used is because it's ignoring convection currents, for example, and that would completely erase the phenomenon they're claiming would exist.
Well, no, the right idea to me would seem to be, though, would be to incorporate the other ideas, but not to leave that out, that because those forces are real. You have to add in gravitational charge segregation to have any theory that is even close to being right, especially in extreme gravitational fields.
But if there's convection currents, it's going to erase that effect automatically. It's just basically like, yeah, if I pour milk on top of my coffee, it might separate, but if it's constantly being stirred, it's not going to separate. The sun is basically stirring because it has these convection currents.
So you'd argue that it's a well-mixed plasma that's at the surface, and that there's effectively no gravitational charge separation then, right?
It seems like that would be less likely because, again, like I say, the convection currents, mostly because since the core of the sun is particularly hot compared to the outer surface, that is going to naturally produce convection currents in the fluid that makes up the sun.
See, I'm pretty convinced that that's not the argument, though. The argument actually is just ignoring. And when you get to,
well, like I say, if the argument requires ignoring a phenomenon we know that happens in the sun, then there's a reason the paper's ignored.
Yeah, except that when you get to like more compact and especially cooler and more compact objects, then even if you did want to ignore it completely on the sun, you still have to. You especially have to add that in with, even in the case of like, just forget about exotic objects, but just like a cooler dwarf star where the gravitational field, we know the gravitational field is stronger, and then you have less of those radiative effects. There's still, I'm arguing that object, that logic, which is straightforward, has been completely ignored, not taken into account in any of the models of gravitational collapse.
Just for example, when you speak of compact objects, but not necessarily exotic, you're thinking things like white dwarfs?
Yeah, like black holes and neutron stars are, I mean, you do have some, even, I'm talking even in the mainstream, rethinking some of those ideas, but nobody argues that that a white dwarf doesn't exist. We've got one like in our own backyard, for example.
Yeah, around Sirius.
Right. So, but in compact objects, in very dense compact objects, we should have extremes of gravitational charge segregation to deal with. And I'm saying, I would be content if I saw articles saying this is why we should ignore that concept, but that's not what you see. They are ignoring it. They're not saying why they should be able to ignore it. They literally, again, the point of that article in the mainstream was to.
Your audio cut out a bit again, but I think one thing I would think in responding, for example, with, say, neutron stars, the reason we wouldn't see that sort of charge separation is because the neutron stars mostly, well, neutrons that have no electric charge. It's also not going to be behaving like a fluid. There's also a huge amount of spin. The neutron stars were able to like detect. They seem to have these incredible angular velocities because they still have basically the angular momentum they did as a full star, but now compacted down to something going from the size of our sun, about 100 Earths across, and then compacted down to something the size of Boston, and still keep all that angular momentum. Yeah, it spins super, super fast. Or if we want to stick maybe with something that isn't just neutrons, so like, say, a white dwarf. There, though, again, it's not something fluid, so you're not going to have that same separation. It's going to not even be a plasma. It's going to have like electrons and protons hanging out together. And then, of course, under extreme pressures until the point that if it reaches what's called the Chandrasekhar limit, and then the gravitational pressure is so great that even the Fermi pressure that tries to hold it up collapses, and then it collapses into a neutron star. So again, I think the reason this is being quote unquote ignored is because the proposed mechanism can't exist in these circumstances, and we understand the underlying physics of why.
That I'd like to see anyone else arguing that in the mainstream. Not forget about anyone in EU. I'd like to see where those arguments are addressed, that we can ignore, gravitational charge segregation. I'm open to that it's been dismissed rather than just kind of swept under the table, but I don't see any evidence that it's been legitimately dismissed anywhere. I see that as those authors also, they spent more time, obviously, than I have in digging up to see from the 1920s where that argument went and why it disappeared, and their findings were it just vanished. Not that it was successfully dealt with as a way like we don't have to worry about it. No, but it was just gone.
Do you remember what journal that was published in, by the way?
Astronomy and Astrophysics in early 2001. I think it was submitted in January, maybe accepted in April of 2001. So, but it was definitely Astronomy and Astrophysics. It's a good read, even if.
Okay.
I recommend you read that. If that's all I can convince you on, is there's a good article that you might not be aware of.
Yeah. One other quick thing as well. Have you looked at that article on Google Scholar to see citations of it?
Citations of it since then. Yeah, I should see where it's been taken from there. It hasn't come up a lot though, and like I say, there's no mention of it in any of the like simple stellar astrophysics courses. It should be that should have been addressed, at least the concept as adding it into the mix, whether it's dominant or not. And no, so I'm gonna do that. No, now you got me intrigued, like where it's, if I could see that was actually dismissed or shown to be wrong, or shown not that it's wrong, but that it didn't matter, then yeah, that's fine. I just don't think that's what happened at all. I think it really was ignored. But
Okay.
you and I can pick that up.
Yeah, I think basically I would first jump to Google Scholar because it tends to scan the web for other publications that cite other ones, or otherwise, you're probably familiar with the archives.
Yeah.
All right. And for the audience, archive or archive.org, archive spelled with an X because science likes the letter X. It's basically a place for scientists to have pre-publications of their work. A lot of the articles will go up there and they might never actually be published in a journal, but they're ways of just like communicating with other scientists. Some of them are there as preprints before they go to other journals such as Astronomy and Astrophysics or Nature or whatever else. The key thing, though, is that for a regular person without a university access, anything like that, it's completely accessible for free. You can read all the papers you want, PDF format, and all the thing you have to have is an internet connection. So there's a lot wrong in academic publishing when like journal articles are like $40 to read the abstract and absurd things like that. But this is just straight up. You can read the paper for free, and it may have some changes versus the published version, but it tends to be, written at a more professional level, with exceptions, but more or less. So I would also say I would probably look and see in the archives who else has even mentioned this paper in passing or anything.
Yeah, I spent a lot of time on that. Obviously, I mean, it's an advantage to being not professionally employed in my field, in that I have a brain dead job where I can research anything I want. When you know this, if you're in an academic field, string theory or something, and you kind of get into a dead end, if that's what you're paid to do, you're going to just keep beating your head against the wall. And I'm free to just say, oh, I don't know what's going on there. I'll wait and see if somebody else, and I'll do this totally other thing. But there's a huge amount of really interesting astrophysical, well, just physics literature out there that, like you say, that's a good way to get it too.
Right. Of course, because it is written by scientists to scientists, it will be in extremely technical jargon. So you will basically have to learn another language that's at least as hard as Japanese, it feels like sometimes. And there's a reason astronomers will tend to specialize. So the people that are studying comets will probably have a hard time reading a paper on Big Bang nucleosynthesis or on galaxy formation, because it gets so specialized with such important terminology and important papers that to switch from one section to another, trying to think what a good analogy would be. It's like if you already know Mandarin Chinese and then you're trying to learn Cantonese. It's related, but you can't understand it without trying.
Which also leads to a lot of mistakes in science, though, because even very intelligent scientists in one field that know that language don't know. There's like a lot of times you'll see things almost duplicated in biology that you'll see in space plasmas, but the terminology is so different that you don't realize you're reading the same thing. And that's what I like doing, is reading across disciplines. And like you'll see Bessel functions coming up in laser light beams, where they can make laser light beams spiral around the background magnetic field. So now if you're talking about electric universe, Bessel functions, you see why those are interesting articles to delve into.
All right. By the way, since we've mentioned Bessel functions a dozen times, do you want to say what Bessel functions are? Again, for the sake of everyone listening.
Yeah, well, again, kind of a complex mathematical solution, but basically the logic to it was just when you're talking about individual elements self-interacting, that was what got these guys to that idea. And it leads to really just but the Bessel function in cylindrical coordinates leads to really bizarre behavior. Ironically, though, the Bessel function in spherical coordinates is what nuclear guys like to use. So that doesn't mean that it's right, but that means that you might be onto something. Like if someone in the EU says that that's how it works, you shouldn't be shocked that well, that's a really bizarre, counterintuitive mathematical function. It doesn't apply. Well, no, it probably, there's evidence that we use that in, in other areas where we know that's right. So.
Yeah. Yeah, I would say just for the sake of the audience that that Bessel functions are basically solutions to differential equations that have some sort of spatial symmetry. So, for example, spherical Bessel functions is when your distribution is spherically symmetric, and then the solutions to the differential equations fit with that. Cylindrical Bessel functions if the distribution is cylindrically symmetric. That's especially useful if you're talking, like, say, a line of charge, and you're trying to describe the electric field around that cylindrical Bessel functions is probably a way to have those solutions solved. And it's called Bessel functions because there was a mathematician named Bessel who did all the hard work of solving those, so I didn't have to, and saved me probably months of blood, sweat, and tears. So I think we've talked a fair bit about the sun, but since you've distanced yourself on some points of EU, people on others, but I think we probably want to talk about the sun, the main driver of what makes it shine. Like, the most prominent names I come across in EU talk about it being due to ultimately electric currents. The mainstream view is fusion. What would you say?
Well, yeah, even in the electric universe community, see, they since that is outside it's not the standard model. The standard model is pretty much one thing. In EU, there were various, right from the beginning, when people were seeing what looked like electric effects, there were different ideas on whether the sun is as radically as whether the sun is positively charged, negatively charged, or net neutral with charge segregated layers. Those theories were all out there. Theories of whether current flowed through the sun or to the sun, which obviously requires net charge. I mean, there's not really one EU theory on what this, the way the electric sun works. So I try to stay. I keep up on where they're going, but I don't really have a lot to add on that. And I do see that that's the most. I try to stay outside the heliosphere. I mean, there is a double layer at the heliospheric boundary. That's becoming more and more clear, but I stay outside of that. For lots of arguments inside, lot of bit to consider that I do and don't.
Okay, just because,
really too much to comment on.
Yeah, I have to say, in some ways, I was a little bit disadvantaged because I didn't find much web presence of yours to see your views articulated. So when I look up EU, I'm mostly seeing things like what Jurgens had proposed or what Scott proposed, where basically the sun is, to be a little bit simplistic, an oversized transistor with gigantic currents coming into or out of the sun. And in particular, with Scott's model, that we're talking, like trillions of amperes of current traveling through to power the sun and make it as bright as we see it.
Right. Now, I mean, pretty much anyone got to at least have the idea. I think in the EU, everyone that's reasonable knows that there can't be this huge discharge over time. I mean, the sun doesn't change that radically, and in any way that you could say that the sun is vastly sweeping up opposite charge. I mean, I don't think too many people are going there. There's an idea that there's inductance involved, and that current in through the poles, out through the current sheet. That's one of the models you expressed, with still no net charging or discharging of the sun. And I know there are those out there that are saying that it is charging and discharging too, but now you could make a case for current flowing with Don Scott's idea of capacitance, current flowing in and then building and out, like what we see with the asymmetry of the solar cycle between the north and south. The south, there's like definitely a lead in the north, and then followed by, you know, a delay in the south, and you could make that work. Again, I try to stay out of that that debate. But one thing to consider that I am convinced of in the models, like when you look at all the observations of the solar wind, where it goes from like a Parker spiral that you see in the mainstream literature. At times it stops, and at times it has the shape of two oppositely directed cylindrical flux tubes. And what you're seeing, if you draw these out, you're seeing a spiral shape, a barred spiral shape, or just an amorphous, not those clear flows. The same shapes we see on the galactic scale for spiral galaxies, barred spiral galaxies, but the sun's current sheet does take those shapes. So that's something to, however you want to explain it, it's, again, you have to really go into the literature to see exactly how they're mapping it out, but then you'll see the correlation there. So to me, that is worth exploring, but that does mean, well, I'll let you decide what that means. But see, one thing I am convinced of too is that when you look at different scales, you're not going to see the same thing. Even if this idea that the universe is kind of fractal, it's not going to appear that way, because what you're looking at is what you see is dependent on your scale. And so, but you're going to see sometimes, like in that case, almost exactly the same behavior, where you're just seeing different aspects of it.
This brings up then the solar wind. So one of the issues that comes up with the various observations that the sun either has a giant charge or is being charged, or has some sort of net charge in some way, or dislocation of that. The solar wind, which is basically charged particles shot off from the corona of the sun, it looks like when we try going out and measuring it, it's equal amounts positive and negative. It doesn't have a net charge overall, which would go against the sun having any sort of net charge. If it did, we'd expect it to have some sort of discrepancy between basically how many positive and negative charges are shooting out in the solar wind, but we see equal quantities.
Yeah, again, that's one of the things I have issue though, is what we have confidence in measuring. See, there's all the assumptions that we go in with the assumption that the EU idea is right in the mainstream. I'm talking like that Earth doesn't have a net charge, or the sun, and your space probe doesn't have a net charge when it starts out, and it's not shielded from the environment, or that the way a probe works is it's supposed to measure a voltage across as if the whole thing isn't shielded, it's ridiculous. I mean, that part you do know that what they're claiming to measure with those probes isn't even close to being right. They're not allowing for the whole thing to be shielded from the environment. So right there, it's actually, their measurements are warped. They're not going to be right. You know, doesn't prove EU ideas, but these assumptions that very simply, even if forgetting about shielding and plasma double layers or any of that, obviously if a space probe had a net charge at all, positive, negative, and was flying out in space, what it would detect as far as like charged particle counts, well, that's really going to be different, whether it's positive or negative charge compared to its environment. And again, like I say, the measure of voltage drop across a probe, the whole probe it, it's not right. They make too many assumptions for that data to be accurate at all.
Well, for that to be the case, there would have to be some amazing coincidence that the probe would have to have the exact voltage to perfectly cancel out the effect, so that way it looks like there's no net difference in the charges coming out. And as for assuming the Earth doesn't have a net charge, it's not so much an assumption. We can measure electric and magnetic fields, and we can tell there isn't a gargantuan charge here on Earth. We would have noticed.
Well, I mean, we have charge double layers. I mean, like people that are into studying volcanic activity know that where there should be not gravitational, charge segregated layers based on compressive ionization and stuff like that. And then also in the surface of oceans, they know that people in the individual fields know where you have to have charge segregation and local electric fields. But your average geologist and your average oceanographer and your average astrophysicist don't get together very much and talk about, and your atmospheric scientists, again, if you know what compressive ionization does and the effects that, there's people that are just focused on nothing but that, like what happens deep underground when there's enough.
But here's the thing, though, like, we have tools that measure electric field, and when, especially with making electronics, we go out of our ways to ground ourselves. Like, just for an example, for a short, relatively short period of time, I was part of the Atlas collaboration at CERN, and I was working on some of the electronic components that were going to go into the optics for the detector there, which is going to go right next to the beam. When I was in the clean room working electronics, one of the things I needed to do was ground myself, because as walking around, I can build up a charge and fry the electronics. So going out of our way to make sure there's like no voltage differences in that environment. So it's not like, if people were completely ignoring, the buildup of charges on our probes, they probably wouldn't work, because they would have been fried before they even were put on the rocket. And I can speak from experience, because I did that to the electronics. I screwed up one time. Don't tell my boss.
Right, but even like with, I know I'm getting way off base, but like even with the, like what you saw with the Challenger disaster, when they looked into that was a prediction that if there was this electric field they were going through, and what a lot of people didn't see in the news is that they had that very issue of like discharges from the tips of shuttles well before the one that finally blew up. And that's a prediction. If you're going to fire a solid booster rocket that leaves metallic conducting particles, you're going to have that happen sooner or later, especially it was the ideal conditions that actually aren't ideal. If you understand electric fields and leaving a conducting path, you know that a little bit of breeze or crosswind is what you want. You don't want a nice calm day. I'm going to argue that was actually a discharge. That was once the voltage difference got high enough across that conducting path, that's when the thing blew. But the evidence is out there, not in that one, but the ones before that. How are you going to explain what was going on? But that was the theory argued way back, as if there is a voltage difference with height in our atmosphere. And again, you could be grounded, but grounded compared to what? That's the whole issue with the space probes.
I have to admit, this is the first time I've heard this sort of thing about the Challenger, because the explanation for that is usually that one of the washers related to the fuel was frozen. The O-ring, that right. Was somewhat famously demonstrated by Richard Feynman to Congress to show what problems it had.
But if you look at the earlier videos of that, you see that clear behavior of the shuttle, like just sparking at the wing, because they all had cameras outside to record the whole launch routine. And you see that going on. And then when you just read you see why they didn't have as many problems in liquid fuel rockets. They had problems with liquid fuel rockets, obviously. But with the solid boosters, that with metallic particles, that's like a perfect example of what you wouldn't want to do in an electric universe, but
one thing though that there's a different explanation that most engineers seem to go with the O-ring that I mentioned, and secondly, if this was a problem, then shouldn't we see this sort of phenomena happen with the hundreds of other shuttle launches over the decades?
Well, they're in early days they used more liquid fuels, and now we have a lot more accidents than you think. Other countries use solid boosters, and we always blame their, North Korea doesn't know what they're doing. Their engineers are stupid, and that's why their solid booster rockets explode all over the place. What I'm saying, it's not uncommon behavior, and that.
I'll say this much: we don't have great data from North Korea because of the society there, but we have literally hundreds of launches of the space shuttle with its solid rocket boosters. And if this were a phenomenon because of something fundamental to the atmosphere or the universe, then it shouldn't have been this one-off thing that seemed to relate to an extremely cold day that hurt the O-rings, as the engineers are suggesting. There would have been lots of explosions of space shuttles, not one.
Well, what I'm saying though is that there were discharges, and in other ones, evidence of discharges from the wing. What you have to realize would be different is what you would need is if the path is insulated, you don't have an issue. If the path is completely conductive all the way up and down, you're not going to have an issue, are you? If there's a voltage and you're running a wire the whole way, you're still safe. The issue is when you get a reconnection after a buildup, and that's where the evidence lies. I mean, I've watched those over and over to try to, again, with that argument in mind, like when we see all this arcing, what made that one like that? And that's where I'm going with that one. But now we're on a whole different. That's nothing to do with.
But strangely down to earth. All right. And since with these talk of electric discharges, I also remember a lot of EU people have said a lot of things about comets. I don't know if you have any views there.
Yes, ironically, was that my first introduction? No, it was after the precession idea. What got me into the EU first was there was another outside the box, just whole different group talking about precession and ancient knowledge, the way ancient people were so obsessed with precession. But this guy read that precession was caused by the sun's orbit and the whole solar system precessed, not just Earth, which, as you and I would know, that's total bunk. And we know that Newton was right, that precession is caused by gravitational tugs of the sun and Earth. And I knew all that was wrong because this other guy, ironically not a scientist, started making all these points like that. Precession has been increasing for at least 120 years since we've been accurately measured it. We know Newton didn't know that. Newton also didn't know that the moon was slightly, I admit, but drifting away from the Earth. If he did, that alone, he would have said precession is caused by gravitational tugs of the sun and moon, while precession is speeding up and the moon is getting slowly farther away. He never would have done that. But we've patched theories, and a lot of people don't know this. I didn't as a grad student in astrophysics. The precession isn't calculated that way. It's calculated by a formula that we knew how fast it was going in 1 year, and then we add this correction. But even that's not right, and there's people that are figuring out that our correction needs to be corrected. So if anyone tells you that mainstream theory does predict precession right, they're wrong on that. And that's where I started, though, is looking at what was happening, and those ancient ideas that, yes, our whole solar system moving through space. And what got me into it, the double helix nebula. What's the mainstream estimate for how fast that's spiraling? 10,000 years. Same order of magnitude as our 24,000 year precessional cycle. And that's what got me to consider that. I had this very poor grasp of electric universe ideas. I thought, wow, maybe if I'll go here. Maybe the sun spirals like a charged particle, and then it would precess, because we know from a method we do know for precession is charged particles in a magnetic field precess. And a little inclination that might be right is when you're mapping out the long-term, not immediate magnetic field that the sun is in, but the general magnetic field inside, again, the local chimney. It turns out that our precessional axis happens to match our long-term motion within the, okay, again, I had the wrong simple idea that it was Earth precessed like a charged particle. But that's where I got into the electric universe ideas. But then Wall's model, because when he was talking about his electric comet model, actually did explain a lot to me with, I still think it's convincing of that, like they keep saying that water, comets are dirty snowballs. And I know more than most EU people, the mainstream model and what's wrong with it, what's open issues and unresolved things, like with the distribution we need for comets and the interactions we'd need to send them in as often as there's a lot of weird coincidences or improbabilities in the standard model with comets. But his ideas actually made sense for the discharged tail as opposed to the dust tail. That's actually the difference between those two actually was what got me intrigued. So, I mean, there's evidence that they are Birkeland currents and work like Birkeland currents. Again, if you don't have the idea that there's Bessel function, that was the key thing. We shouldn't even be talking Birkeland currents until we have Bessel functions down, because otherwise, that's all kind of a joke. If you don't know what a Birkeland current is, then, or how it works, then obviously you don't even know how to argue whether that is one or isn't one.
Okay, so I do have to then ask the question, if you're saying that you have your doubts about comets having large amounts of water, what about all the spectroscopic evidence that when we look at the tails of comets, when we look at the materials of comets, when we've fired things into and shoot off chunks of comets to look at it, we see and measure the effects of water?
Yes, that was the beauty of his model. See, the electrochemistry part was what really got me. It's not, you're familiar with his argument, is that water is formed there by basically we've got oxygen locked up in rocks. If here you have to put a bunch of people's ideas together, but what's the guy? One of the best mainstream orbital mechanics guys was Tom Van Flandern, before he came up with one of his crazy theories that there was a planet where the asteroid belt was and it exploded, but he was one of the leading experts on orbital mechanics, and he showed why we should only have long period comets or asteroids and not all these intermediate orbits. But that idea would be that a lot of comets would be the same rocks that we see as asteroids, but there is a lot of oxygen locked up in there, and that's where Walt Thornhill kind of came in and said that if there are protons, in the stellar wind, how do we know that there's not? It wasn't that there was water locked up inside. Water is created in the discharge tail. And I find his arguments on that really compelling. So he would say, and there's where the observations come in, like when they crashed a probe into a comet, looking for all this water to be released, and they see this flash. That was his evidence that there was a discharge, but they also didn't see the water. And this is how ingrained this non-EU idea is in the mainstream. NASA's answer to that is we need to build a bigger probe to smash harder into the next comet to release the water. That's how pig-headed that idea is. That
I think I need to throw some caution to that, because NASA didn't say that they saw no water. They saw less water than they were expecting, and were revising the model to say comets aren't dirty snowballs, but snowy dirt balls. They still detected water.
Yeah,
and conversely,
like I say, there's always going to be water the whole time. There's going to be water produced, and if there is an electrical interaction between a probe and a comet, then there's even, if that really is the mechanism for production of water, then yeah.
It's also worth noting we see things beyond just water. For example, we don't see just water ice, but dry ice. We see carbon dioxide, and you're not going to get that from the charged particles from the sun. Incoming protons hitting oxygen isn't going to form carbon.
I've lost track of more of his electrochemistry. He does have a lot of this worked out. I'm not going to argue his point here. I'd have to revisit that. Like I say, I've moved so far away in the last few years from anything inside the solar system.
Okay, because I was also going to mention the soft landing that was done by the Philae lander several years ago on another comet. And well, one of the things is there wasn't a large discharge, as some EU proponents were saying that they saw with the other comet. In this soft landing, it touched, but there wasn't basically lightning bolts. There wasn't X-rays or anything like that you'd expect from some sort of plasma discharge. And we basically now have like these beautiful images. There's in particular from, I think it's called the Rosetta or is the Osiris mission. I'm getting my names a little mixed up. But in observing this comet and having these close approaches, having basically these videos, and you could basically look, and it almost looks like snowfall along cliffs. And this isn't the sort of thing you would see if, water and dry ice is being made on the fly.
On the surface, you mean?
Yeah.
See, that's
right.
That's really the key to argument either way, as far as if you want to talk about future observations.
Yeah.
Either.
Also, additionally, it's also worth pointing out that we've also had many objects come from deep from the outer solar system or even beyond the solar system come in and not give off water at all. So, for example, several years ago, there was the asteroid Oumuamua that it was called. And that one never produced a cometary tail, and it came from, well, we think from another solar system because it had so much gravitational and kinetic energy that its path is totally hyperbolic and, came from who knows where and is going, someplace completely different. But the key thing is it didn't have the discharge. It didn't have the production of the tails that one would expect if we're saying a rocky object being bombarded by the solar wind is going to release that, because it didn't produce that sort of tail at all. So that also seems contrary to that model that you mentioned.
Well, see, that also was addressed by another, and this guy was involved with the EU community, but he's like mainstream. He's sharper than I am. More Eugene Bagashov is like really good with quantum mechanics stuff. That's what he went to school for, and he works in that. And he went in a good deal on the orbit of that and why it should or shouldn't have, based on the path, again, with the idea that the sun is in some current filament. Then you look at the map that they would have for the sun in a current filament, and what it was effectively doing on the way in is it was having when it wasn't even before it was detected, is traveling pretty much along that path rather than any through that radial electric field that they would posit for comets. I mean, so I'm not saying that proves that right, but in that model, you could see why there wouldn't be a tail just from their arguments. You know, it's not like, again, that you're going back to more to the scale I'm familiar with, though, that where you're talking the electric field of a cylindrical filament containing the sun compared to a spherically symmetric field of the sun, and that's what got me intrigued in, like, looking at his stuff and all. But people should know that I mean, there are, again, if the audience only gets this, that it's not all quacks out there. There's a lot of good, you know, physics brains that got hooked because of, not that they take every theory hook, line, and sinker, but there's a lot to be looked at, to be considered by a serious scientist with a physics background, and there's a number of us out there. So, not that, again, there's a number of you guys out there not on that page too. So, you know, I'm not arguing that point. I'm just saying that, you know, it's not all quacks, for sure, even if we're wrong.
All right, so I think we only have about 10 minutes left, but I also see a lot of EU proponents had gotten into this or are very influenced by the ideas of Immanuel Velikovsky. What do you think about any of that?
Well, yeah, it's like, to use an example, when you're going to challenge mainstream ideas like the Big Bang, for example, you're going to get people that challenge it for totally different reasons. You're going to attract people that think maybe some version of steady state infinite universe is right. I happen to be more on that page, more those old ideas. But you're also going to attract creationist scientists that say, no, the Big Bang's wrong because the universe isn't that old. And there's all of them there. I'm one that thinks that a lot of what's wrong in mainstream science now is that even though mainstream scientists argue against the Judeo-Christian tradition, almost all the science now, Big Bang included, came out of an age where the Catholic Church especially ran science in Europe and in the early days in the United States. There were Catholic institutions. That is our scientific worldview. So when, you know, a lot of modern cosmologists like Lawrence Krauss, for example, he's famous for bashing the Judeo-Christian tradition, even though he spouts stuff that came purely with little scientific. It didn't take a lot of evidence in the early 1900s when most scientists were Christians at Christian institutions. It didn't take a lot of evidence to show that the universe was created. It was just a matter of when it was created. But I happen to believe what the Mayans and the Hindus and the Native Americans and all these world cultures have said the universe, if it wasn't infinitely old, it was greatly old, and the creation stories were just local events. And I pinned some of those to, just by the names that they mentioned, to the local chimney structure and local, not even the galaxy, but right here in 400 AU. A lot of creation stories go with that. And all these, obviously, if Hindus are talking about not just yuga cycles, but long, cycles of 24 million years that repeat over and over, and the Mayans with their cycles way longer than our universe. And, I tend to believe that the universe that's more a religious belief than any scientific belief, but I think the universe is infinitely old, and the Big Bang is wrong for that reason. So obviously I don't go to, I do believe in that our solar system wasn't as stable as the mainstream view, but I don't crunch everything, all these stories that we get from history, to try to crunch those into the Judeo-Christian timeline of 5,000 years ago. I think there are recordings of events that happened way longer ago. That's my view on that. But all these other cultures, we destroyed a lot of evidence where, like, Mayans happened to agree with the Vedic, some of the stuff in the Vedic texts, and then pagans in Europe also believed these things. And then when the Catholic Church went around, it destroyed all that and killed a lot of the priests and medicine men and shamans. You can't use then, in modern times, a lack of evidence, recorded evidence of things in the past, as evidence that they didn't happen. And again, clearly ancient people knew enough about the precession cycle that they knew more than Newton did. Newton thought it worked like a spinning top. In the ancient writings, you see that they knew the precession cycle didn't overlap, that when it circled through the sky, it also drifted. They say drifting to the left, but that was in the galactic reference frame. They called the galaxy the sea. But there's evidence that they knew not just of this 24,000 year precession cycle, but that it drifted continuously. And again, that happens to match the motion of stars in the local chimney and that ring of rotating stars. That's the direction that all goes. So they were onto something. Take that as almost a religious belief, because there's no way anyone could ever argue that the universe is infinitely old. Just that it's older than the Big Bang. But no, okay, I'm not into Velikovsky timelines or.
Okay.
That was very long-winded.
I guess just in response that I find it very implausible that there was widespread knowledge of precession, simply because the first people to explicitly have discovered and measured precession don't have it as, the 24,000-ish or 27,000-ish period. Like, the earliest records we have to that is with Hipparchus in about 150 BC, and his measurement, he says he thinks, is roughly about 1 degree per century, giving a precessional period of 36,000 years. 200-ish, 100 years later, Ptolemy tries improving on the measurements and can't. And, that just shows, how difficult it even was to make those measurements, so that other cultures without the same technologies that the Greeks had developed and inherited from the Babylonians, and yet everyone else knew it without the same instrumentation, without the same techniques, and to greater precision than those who were explicitly looking for it, seems initially very implausible.
Yeah, again, that gets to be, then you're arguing against any ancient knowledge of that. But the book, if you're familiar with Hamlet's Mill, again, yes. The beauty of that book is that they don't have a crazy, they're not saying that ancient civilization like Atlantis rose up, or that ancient aliens brought us this stuff, or that shamans tuned in, and they don't go there. They don't even know the significance of what they were seeing. They're just recording all this obsession with precession everywhere, which, as you say, it's not even something that's very noticeable. So why should they?
Well, it's even more than just not noticeable. I mean, you literally just, you can't see with your eyes. The only way you can notice it is with observations carefully made over centuries.
And to know that it's different from one to another would require even over a full precessional cycle to know that, or else be able to compute that. But that's what we're modeling.
Well, that's actually
now.
what Hipparchus did. He had made measurements specifically of lunar eclipses and their distance from Spica, and he looked at observations that were a few centuries apart. Noticed the difference between the sidereal and the solar year that was giving him, and then allowed him to calculate. And with some error, he knew there was error involved in what he was doing. getting a measurement of about 1 degree per century, while modern measurement has it closer to about 72 years for 1 degree of motion change. So, like I say, it's a very weird thing that someone is explicitly trying to make the observations, doing the calculations, and is explicitly said to have been the discoverer of it, and yet other people without the same technologies, without the same recordings of the observations, did an even better job than the people explicitly recording and measuring, is initially implausible. And there's a reason why when Hamlet's Mill came out, it was pretty much universally panned by the history of science community.
Right, but there's a lot in there that has now been. Once you see the mechanism for it, again, if you have the mechanism wrong, you think it's due to gravitational. Like I already showed you why. We know scientifically, you should know why that's wrong. The fact that
I'm saying it doesn't even matter what the mechanism is. If we're literally told by the Greeks that Hipparchus discovered it, that means people before Hipparchus didn't know about it. No matter what the mechanism is, it apparently was unknown and first measured and described by Hipparchus in about 150 BC.
Except in the Vedic text is where it says that it's caused by the sun's. That's where that idea came from. Is that precession is actually caused by the sun's motion through the galaxy, through the sea. But I mean, the sea was the galaxy.
And that means through the sea, the cosmology of that time was the sun went underneath the earth because they had flat earth models.
Yeah, you're looking at a dark age in history that we think.
No. We have very explicit references. I mean, there's a reason Aristotle had to argue for the roundness of the earth and had to make all these observations to prove that. If everyone already knew the earth was round, Aristotle didn't have to make any effort. The fact that he had to put a lot of effort into it, and people even centuries later, like Lactantius, were still denying the roundness of the earth for, unfortunately, very stupid reasons. It shows that the mainstream view, and we see in the cosmologies of like the entire ancient Near East, of a flat earth sky dome cosmology. So if you're saying the sun is moved by the sea, they mean the sea. If we're not going to interpret to mean actually the galaxy, which they don't call that the same sort of thing, that was the major problems with Hamlet's Mill. They were basically forcing the interpretations to match what they wanted, and why everyone else in the history of science community is just like, no, this is just reading into the text.
Yeah, except what they didn't know that they recorded in Hamlet's Mill is the star motions over time, and where precession, where I'm telling you precession is going to take the pole, and where it was, and not where even in Greek times, not what they thought, or not what Newton thought, because his model is wrong. If Newton's model is right, their precessional axis should be pretty much basically the ecliptic axis, pretty close. It depends where the moon is over time. And what they were saying is that whole thing drifts. And I'm telling you that, again, that topic of precession is really what I'm on about. And I'm saying that precession isn't even speeding up. What it is, it's two motions. There's a clockwork precession motion, and the pole drifts, which means when they work together, I mean, you could draw this with your hand. Just make a circle in the sky and move your whole arm to the left. Even if you have a clockwork precession cycle, then it's going to seem to speed up when you're moving in the same direction, and slow down, and that matches mathematically what's going on. But somewhere in the past, people knew that precession had nothing to do with the sun and the moon, and that part is recorded there. And I'm telling you that part is right, even if somebody made it up or at the time and didn't know. Their old model of precession was right, not this Newtonian BS.
Well, then this is a double problem, because you're depending on Hamlet's Mill, which virtually all historians say is bunkum, and then say the ancients knew physics better than moderns. That's a double hard pill to swallow.
No, I'm just saying that they had a better model of they knew the accurate cause of precession.
But like I say, it seems like the evidence is they didn't even know precession existed until Hipparchus. That's why it was said by Ptolemy that he discovered it. It's hard to make a discovery if everyone already knows about it.
That again, that comes from ideas in the West of what we.
It's not an idea. It's just reading what the ancients say. The ancients said Hipparchus discovered.
Not the ancient. Yeah, that's what they say in the West is that we attribute the Greeks to all these discoveries that the Greeks attributed to Egyptians, and Egyptians said it came from much earlier cultures, which isn't implausible, except that it doesn't fit with Judeo-Christian timelines. And when those people were killed, that's where we lost it. The ancient world was all on the page that cultures came and went. There's early writings.
Well, that cultures came and went is something we can observe archaeologically, but it's also worth noting that Ptolemy wasn't a Christian and his work was preserved, and he tells us his source for the discovery precession was Hipparchus, and from what he records from Hipparchus isn't claiming he found ancient knowledge, it's that he made this discovery. No. So he's not claiming ancient knowledge from the Egyptians or the Babylonians. He's saying, look, I found something that nobody else knew before. If nobody else knew it before, it's a discovery, and therefore it can't be super antique knowledge.
A lot of scientists, even in modern times, you're familiar with Modler, am I saying his name right? In the early 1900s, he got that the sun was orbiting the Pleiades, and he supposedly proved it by proper motions and not radial velocities. When he lived, there weren't radial velocities. There were only proper motions from our observations. So now he was right on the path, but how could he have even gotten that by his observations? You can't. If you only had proper motions, you couldn't possibly tell us whether the sun was orbiting the center of the galaxy or the Pleiades or anything from that. So what you don't know is he was also a bigger into religious history and esoteric knowledge than he was in science. So he did the same thing and Newton did this in his day. Newton read a lot of crazy stuff that he wasn't even supposed to have read at Cambridge. He wasn't even supposed to have access to. But you see a lot of his ideas that he came up with on his own. He read those in texts that you couldn't read as a Christian at the time, or if you did, you better not say. But I'm saying this has happened as recently as the 1900s with Modler, with Newton before that, and all the way back. There's scientists that seem to have made this awesome discovery, but no, they didn't. They read it and then just worked out the details,
Well, again, this is all completely irrelevant because what I'm saying to you is it's attributed to one particular person, not in deep antiquity, but in the historical time period. And we know how he did his observations. He actually says what observations he used, which we can date. Mm-hmm. He uses a technique for mapping out the sky first developed by the Babylonians in about 400 BC. And the reason we also can tell when the Babylonians develop it, because we also have their records. So we can put together and see the Babylonians didn't have this concept of precession. It doesn't exist in any of their writings or records. And we have lots and lots and lots of astronomical diaries from them. So any effort by the Catholics, Protestants, or any other religious group failed to cover that up because we have now thousands of these clay tablets. It's not in there. Hipparchus doesn't use the Babylonian records for his observations to measure precession. He uses Greek observations, and we can date when those are, and we can see that that's why he was being attributed as the discoverer, not that he found it from somewhere else. And again, if he discovered it, that means it wasn't previous knowledge. And so that it was somehow known in all cultures in great antiquity is on its face absurd, because if it were really the case, then it wouldn't have had to have been discovered. You don't discover water is wet if everybody already knows that.
Yeah, that part. That part, I won't even argue. I definitely, I'm fully convinced that we've lost. Again, I'm not crazy enough to say where ancient people or how they got it. I'm absolutely convinced that they had knowledge that we don't have. For example, the idea I told you about, that local center Arcturus, I can show that. That's in my wheelhouse of where I can prove it. It's not something you'll read in any mainstream. I could prove it to you in minutes. I got that idea not on my own, that was the center. That's out there. Somebody knew that. I didn't make that up. All I can do is show you that absolutely is the case. Again, now once you have that, and I'm going to argue that Hipparchus did the same thing, once you have the idea in your head, if you think for a minute, for example, with Arcturus, that I just tried all these different stars and reference frames and found that, I didn't. I actually went in skeptical, like there's no possible way we could be orbiting Arcturus based on, I know enough about that star and its mass and its distance, but I read it, and just to disprove it, the only thing that even made me entertain the idea is that we have this really high proper motion and no radial velocity, which is consistent with one of us circling the other. I mean, that's like the sun, no radial velocity towards us, but a proper motion. But then when you look into it and you try it for a reference frame, bam, all these stars that have these random peculiar motions in our reference frame of like plus or minus 12.5 kilometers per second, they drop to, like the sun's is actually unusually high in that reference frame of 5 kilometers per second. The star Altair, which turns out to be, we're 36 light years-ish from Arcturus. Altair's 38. We're 36.7, they're 38. That star only has a 1.4 kilometer per second radial velocity from Arcturus. And you can go all the way around and find that there's this arc, or maybe it's a circle, I haven't mapped it out, but there's even weirder, like Barnard's star, you're familiar with that one. That's the weird star in our reference frame. Insane radial velocity, insane proper motion. In the Arcturus reference frame, radial velocity drops down to like 12, which is just random peculiar motion. That star is a center. The only reason we haven't figured it out by now is two things. One is we know from our theory that there's not enough mass there, and the idea is impossible to even entertain, even though it's in the ancient knowledge. The other reason that we didn't
So I have to stop you there, because if you're going to say the ancients had knowledge that the sun was orbiting Arcturus, even though, again, like every single ancient cosmology was flat Earth with the sun and Earth and the stars going around the Earth.
Well, how do you do when in the name?
If you're turning a flat Earth cosmology and turning it into the sun orbiting another star, that is you forcing those ancient myths to conform to something else.
Well, when they name another star that we do happen to be circling, or stars around us are circling, when they name, like with the Pleiades, in a lot of traditions, the star Alcyone, one of the names for it even was a central sun. They didn't know about supposedly the rotation of this belt of stars around us that is.
If you're taking the name central sun as an entire premise in a cosmology and ignore everything else, that means you are going to fail to interpret these ancient cultures correctly.
Well,
when we look around the world, and over and over and over again, their view was very consistently a flat Earth. I mean, even in China, until the Middle Ages, basically until Europeans had provided some new evidence for them, they thought the Earth was flat for many thousands of years, and this was a very advanced culture as well.
See, again, that's what we learn in school. What we
no, this is the actual Chinese records. I've read them.
Yeah. Well, what I'm saying, what we have,
and it's not because the Catholic Church burned all of China down. Not even close.
What we can look at is ancient cultures and their navigation around the world. And what you have to realize is that to be able to navigate around the world, when we know people did this, you have to have, it's impossible to do that kind of navigation if you don't have the smartest of our flat earthers isn't going to be able to navigate around the world using the sun and stars with no GPS. no compasses even, and just no accurate timepieces. How did they do it? They had to have a fundamental assumption that the Earth was spherical. Even if you wanted,
But that's not what they said. They say the exact opposite. There's even Chinese records where they actually try measuring the distance from the ground to the sun and basically have the sun at like the same level that modern flat earthers will tell us. So like even their quote unquote scientific treatises treat the earth as flat and the sun as some measurable distance away. And again, this is in a highly advanced culture with writing, so we can go back and check what that's there. We can look at Babylonian writing, we can look at Assyrian writing, ancient Egyptian, ancient Greek, over and over and over and over and over again. And of course, in the old biblical record, it's a flat earth with a sky dome. In particular, like the biblical account has the earth being held up by pillars with a dome of basically something metallic holding up the waters from above. So that way, they can be opened up occasionally, let rain in, et cetera, et cetera. That was the mainstream view for pretty much every single ancient culture until the first scientific revolutions of antiquity and then the modern times kicked through and provided more accurate maps and more accurate techniques for knowing the actual shape of the earth. And it's not because also like the Chinese had ships, they were not going around the world, but they were definitely sailing to the South Indies, to Japan, to Korea, as far as India, things like that. And somehow, for many, many, many centuries, they were totally fine with a flat Earth map. Now, you're right that if they had a round Earth map, they probably would have even better navigation, absolutely. But that they were able to get around does not mean they had the correct geography. And if in the writings, in the cultural memories that we have preserved, that we can check, and they're all coming to the same conclusion that we see in like the ancient biblical version, then saying no, they actually thought the earth was round, but they wrote everything as if the earth is flat, is basically forcing our views onto their text. And I want the ancients to speak for themselves.
Okay, I think we've gone over a little bit of over 2 hours, and I think those two statements that you both just gave, Jem, I think your last statement, Dr. Adair, I think your last statement you just gave, I think those are perfect concluding statements to the debate. I thank both of you for joining me today. It's been very interesting. Looks like a lot of people enjoyed it in the chat. And even people in the chat actually were debating each other a little bit.
I saw a little bit of that. Apparently, the most fun was happening there, unfortunately. All right.
Okay, everybody. Yeah. I'm going to play the outro now. I thank you both again for joining me. This has been fun.
Thank you for having us.
Thank you. Yeah, thank you.
Hello viewers, thanks for watching this video from the History Valley YouTube channel. Please don't forget to subscribe and hit the notification bell. And if any of you wish to further support this channel, please consider checking out this channel's Patreon page and becoming a patron, and or donate through PayPal or through Super Chat during a live stream. Thank you.